Thanks. And let me also add my thanks to the organizers as well. It's been a really fun conference and program so far. So today I'm going to be telling you about this ongoing series of papers on the world-line quantum field theory formalism, which I've been developing together with Jan Plefke, Jan Steinhoff, and Gustav Jakobsen, all three of whom are here in the audience. And the idea is we've been trying to use this formalism to describe scattering of spinning black holes and neutron stars, starting from the world line perspective. But before I go into the detail on the formalism, let me start by just giving a little bit of context for what it is that we're doing. And I think hopefully most people are quite familiar with this by now, but let me say it again. So the idea here is we're interested in the in-spiral phase, the merger between black holes or neutron stars. And the idea is that the problem that we're looking at is closely related to the problem of black hole scattering. We've learned that these two things are very closely related to each other. The advantage of thinking about a scattering event as opposed to an in-spiral event directly is that it can be more natural then to think about this post-Minkowskian framework where you expand as a series only in g Newton, as opposed to when you think about an in-spiral, you often work in the post-Newtonian framework, as we've heard, where you expand both in g Newton, but also in the velocities of your black holes. So for bound orbits, this makes sense, of course, to work in terms of the post-Newtonian framework, because we know from the virial theorem that gm over r and v squared over c squared are of the same order. But what we heard from Jan Steinhoff earlier in the program was that where a post-Minkowskian expansion might make sense, in addition to scattering events, is, for instance, for highly elliptic orbits, where you can imagine when the black holes come very close to each other, you now have high velocities. And in both cases, we're interested in observables. So for a bound system, one might be interested in things like the binding energy, the periastron advance, and of course the waveform, which we want to measure. In the unbound situation, you could be interested in the momentum impulse, so that's the deflection between your black holes, the scattering angle, if your motion is planar, or indeed the waveform again. You can also get a waveform from an unbound scattering event. And we know that it's possible to map between these kinds of systems. One very conceptually simple way is by looking at a Hamiltonian. You look at your unbound system, use it to engineer a Hamiltonian, which you can then in turn use to describe the bound system. But there are now more sophisticated techniques that we can use. So for instance, we have these kind of bound-unbound mappings, which have been studied by a number of different people, which allow us to go directly between the observables. And that's the sort of approach, that we're going to be taking. Yeah. So what we're going to be doing then is we're going to be using this WQFT formalism. And whereas a lot of people have been thinking about using scattering amplitudes in quantum field theory, we've gone down a slightly different road. And the reason we use this WQFT is because we like to avoid the subtleties associated with the classical h bar to 0 limit. We don't want to have to go through this process of thinking about, when we look at our loop amplitudes, what's the quantum part and what's the classical bit. So what we do is we start from a theory, in this case just a Menon spinning, I'll talk about the spinning in a moment. We start from a theory which is defined by the world line. So we have our bulk action describing the gravitons. We have then some gauge fixing term, which we add to this thing. We don't really need to worry about. And then we have a couple of world lines. And this is entirely equivalent to the usual form of the world line action, which is just an integral on the proper time. It's related to the polyaccord form of the action. But where this is different from, say, more standard world line approaches, where what one typically does is just performs a path integral on the graviton. You integrate out the graviton, you get an effective theory, and then you solve the equations of motion for your deflection. What we do is we integrate on everything. So we have a field theory now where we have both the deflections of the black hole, z, from the original straight line trajectories, and the graviton, h mu, and we think of both of these as propagating degrees of freedom. And the way that we get observables then is we think about them as expectation values of operators within this formalism. It's quite a formal way of looking at it, but in practice, what it actually amounts to is we have a set of Feynman rules which describes the propagations and interactions between these z's and these h mu's. And the real advantage of this approach is the directness. The way we get the classical physics is we simply focus on the tree level. Within the WQFT, the h bar expansion is literally the loop expansion. So that means it's extremely simple to get the classical physics. We just focus on the tree-level diagrams. So with the basic outline given, I'll now move on and look at how we introduce spin into this formalism. So the way we do spin is we take our world line action and we generalize it by introducing these Grassmann-Odd vectors into the theory. And what we have here is this n equals 2 supersymmetric world line theory. So in order to find the spin tensor and the Pauli-Lubansky spin vector, we find that the spin tensor can be written down very straightforwardly like this. It's just an outer product between the psi and the psi bar in this theory. And then, of course, the spin tensor is closely related to the spin vector. So one way that you can quickly convince yourself that this is a sensible definition of spin is if you work in the first order formulation, you have your Poisson brackets between psi and psi bar. And what you can do is if you think of S mu nu as a composite built up in this way, you can just quickly show that this is true. So what you see then is that the spin tensor satisfies, the usual Lorentz algebra that you would expect, which tells you that this looks like a sensible definition. However, this particular world line action is only going to be good up to order spin squared. If we wanted to go to higher order in spin, what we then need to do is we need to start adding more of these Grassmann vectors in order to account for the higher spin. What's really interesting, though, is that when you look at this n equals 2 supersymmetry, which we have on the world line, it corresponds to the existence of some conserved supercharges. And these actually, it turns out, have a very natural physical interpretation. So the first one, p squared, is just energy conservation. The next two, the fermionic charges, p dot psi and p dot psi bar, these are the interesting ones. So these, if you take this definition of the spin tensor, these correspond literally to the spin supplementary condition. Specifically, though, this is the covariant form of the spin supplementary condition that we're looking at. Finally, psi dot psi bar, the conservation of this thing, tells you that the magnitude of S mu nu is conserved over the course of the motion, or alternatively, the magnitude of the spin vector. Now, one final thing which we can do is we can add these finite size corrections to the theory. And this is interesting if we want to generalize. Oh, gosh. This is interesting if we want to generalize to think about neutron stars, in addition to just having black holes. So we have EAB, which is now this electric tensor of the theory, which just contains the Riemann tensor and the momentum twice. So one question which you might well ask is, okay, well, I have this very nice looking theory here, but how do I know that this thing actually describes a black hole? I mean, it's not easy to see just off the top of it. The easiest way to see that is if you just derive the equations of motion from this theory. You'll see then that the equation of motion for S mu nu matches precisely what you get from the so-called MPD, Matheson-Papapetri-Dixon equations, at least through order spin squared. So from that point of view, this is a perfectly sensible thing to do. The reason we like to write the action in this form, in addition to the SUSY, which is quite nice, is that we have this nice kinetic term here, which we can now use to have propagation of our spin modes on the world line, in addition to the propagation of these deflection modes, which is coming from the first part of the action. So that's what we're going to be using, and that's what the setup is going to be, roughly speaking. So now I can show you my first example of a calculation, which involves the WQFT. And what I'm going to do is I'm going to calculate the waveform for a scattering of two spinning black holes up to quadratic order in the spin. And the way that I do this is I draw the sum of tree-level Feynman diagrams, where now I'm looking for the expectation value of h mu nu. So I draw all the diagrams that have a single outgoing graviton. And as you can see, in addition to having interactions and propagation involving the graviton in the bulk, I also have interactions and propagation on the world line. So in this first diagram here, you can see we have one of these deflection modes. So literally, you can think of this as the second world line sources a graviton, which then gets captured by the first world line, causes a deflection to propagate along the world line, and then finally it sources the graviton, which gets radiated out. In this diagram, what we have is one of these spin modes being propagated on the world line. I give the thing an arrow because we have psi and psi bar, it's complex. Finally, we can have a two graviton vertex on the world line. And if you were to look at this from the standard well, maybe not standard, but the more conventional now QFT point of view, the way you'd look at this is by thinking about a 5-point amplitude. You'd take this 5-point amplitude and you'd take the classical limit. The advantage of looking at it from the WQFT point of view is that there's no classical limit here. You are essentially just writing down the answer immediately for this waveform. In order to get to something that we can actually measure, though, the time domain waveform, what we need to do, though, is we need to integrate on the energy. So what we basically do is we take our graviton, we take its momentum k, we basically just point it towards the observer, who's at some distance r far away from the point of scattering. So you see you have this vector rho, which points towards the observer, the direction x. We have omega, which is the energy, and then we just perform an integral on omega. And this just looks like a Fourier transform. And what you're left with then is an answer where you have a waveform now, which depends on the angles, which point towards the observer, theta and phi, the relative velocity, the impact parameter, the masses, and the proper time. And what's really cool here is, so there's been some work done at AEI. This student, Babi, together with Niels Vu, have actually succeeded in producing a simulation of this thing, which I'll just go ahead and show you right now. So, whoops. Here we go. So here we have the scattering of two black holes, and we have the waveform that's produced by said scattering. And there's one other simulation in just a moment. That's the other one. Actually, Dummy's produced a whole bunch of these plots, and they're really quite cool. Anyway, so he has a YouTube channel where you can look at more of these things. So what you were literally seeing there is you were seeing the plot of this F plus. So what you had, so it's the F plus component. You're seeing it evolve in time, and you're seeing projected this heat map of the waveform being produced in the theta and phi directions, literally in three-dimensional space. And that really is the thing that we measure. It's really quite cool. So I can point you to that YouTube channel later if you're interested in seeing more of these things. But that's just one of the things that we can calculate with the WQFT formalism. We can go on and look at other more general things as well. So using this waveform, which I just mentioned, we can proceed to look at some secondary observables. So for instance, we can obtain the radiated form momentum and the radiated angular momentum produced by the scattering of these two spinning black holes. And these formulae here are quite conventional. So what we do is we take the waveform, time derivative, we square it, and we perform an integral over the retarded time and over the three-dimensional solid angle, which I call sigma. And it's a similar procedure for the radiated angular momentum. Now, this formula here, I believe only holds in the center of mass frame. But recently, there was this very nice paper by Manohar, Ridgway, and Chaoshen, who I think is going to be talking about a more general version of this formula later on, which applies in an arbitrary frame of reference. But in any case, we can do these integrals. And in the case of the radiated angular momentum, it's fairly straightforward. And what we can write down is a formula for arbitrarily aligned spins for the radiated angular momentum in such a process. And it turns out to be proportional to this universal function here, which if you've looked at these things before, crops up quite often in these calculations. I'm glad to say that this formula has actually now been confirmed to all orders in spin in this very beautiful paper by Alessio and De Vecchia, which came out just recently. And they showed that basically, if you go to higher orders in spin, the structure is very similar. You have the same universal function, but then this spin-dependent piece basically just continues on up to higher orders. So that's all entirely consistent. In the case of the radiated form momentum, it's a little bit trickier, though. It turns out that these integrals are a bit tough to do in a post-Minkowskian expansion directly. So the way that we did this is we expanded in a post-Newtonian series. So if you look at the zeroth component of this thing, you get the radiated energy, working in the center of mass frame, that is. And these are the leading order terms in a PN expansion of the radiated energy produced by the scattering of these two spinning black holes or neutron stars. You see we have the spin vectors here defined in their respective center of mass frames. We have these C coefficients, which are the numbers parameterizing these finite size deformations to the black holes if we're looking at neutron stars. And then we also have to sum on the two different, on the 1 and 2, the flipping the two black holes. So that is basically what I wanted to say about the waveform. What we've really been very interested in recently, though, is looking at this third post-Minkowskian order calculation. So this is the work that I very recently did with Gustav Jakobsen. And what we did here is we were interested in calculating these observables, the deflection of the black hole, but also the spin kick, which we think of as the change in this Grassmann spin vector. And the way we do this now is we draw the diagrams that have a single outgoing line, but this time it's a line on the world line. So these diagrams should be thought of as schematic. These solid lines could be either these deflection modes, Z, or they could be the spin modes. I just draw them together like this because otherwise there'd be a lot more of them. So it's the same kinds of diagrams that you have. They're very similar for if you're calculating delta P or delta psi. And as you can see, I've separated them here into two categories. So the top category here, these diagrams represent the test body limit. And you can kind of see that quite easily, actually. So what you can sort of imagine is that the diagrams, you imagine the dotted line on top represents the test body. The dotted line on the bottom, that represents the much heavier black hole. And what you can sort of see is that the much bigger body is essentially just firing black holes at the test body. The heavier body doesn't move. It doesn't do anything. It just sits there and sends black holes at the test body. And you can see that all these deflections and all these things, they're all happening on the upper body. And what you should realize when you look at these diagrams is that, I mean, you'd certainly be forgiven for thinking that these are two-loop diagrams, because they really do look like two-loop diagrams. But they're not. They're tree-level diagrams. When you look at them, what you sort of need to do is you need to forget that this dotted line exists, because the point of the dotted line is it's just a reminder that these interactions are happening on the world line. So what that means is they're not conserving form momentum. They're only conserving energy. So even though these diagrams should be thought of as tree-level diagrams, we do still end up with what you might call loop integrals. What's happening here is we need to integrate on the momenta of all the gravitons that are being exchanged inside these diagrams. But because on the world line we're not conserving momentum, we're only conserving energy, that means that these integrals actually end up being non-trivial. And they end up corresponding to what in the amplitudes picture you would think of as your loop integrals. It's quite an interesting interpretation, actually, how you can get loop integrals, but while still drawing tree-level Feynman diagrams. The other diagrams which I've drawn down here, these correspond to the comparable mass scattering. So now you can see we've got deflection modes propagating on both of the two world lines. So now we can see that the two black holes are non-trivially influencing each other in some sense. And of course, there's a lot more diagrams. And as far as the calculation is concerned, these are the more difficult ones to actually deal with. Okay. So then, of course, we have to do the calculation. And as I say, it's very straightforward. The procedure is you draw all these diagrams, you have your Feynman rules, you associate expressions, and now you have to do your integrals. And even though they're tree-level Feynman diagrams, the integrals that we obtain are still this family of two-loop Feynman integrals. And what we do is we regulate our intermediate divergences by using dim reg in d equals 4 minus 2 epsilon. Now, I don't want to go into too much detail about the loop integrals because, well, either you know how to do them, in which case it's not interesting, or you don't, in which case it's a very long discussion. What I will say, though, is the following. The general way in which one approaches these kinds of loop integrals is you don't try to do them directly. What you do instead is you look for linear relationships which are satisfied between different integrals of the same family. And the most important kinds of these relationships are the integration by parts relationships. And there exist algorithms on the market. The one that we use is FIRE, also in combination with light red. There exist tools on the markets which automate this task of finding all these linear relationships. And in general, what you want to do is you want to take all of your loop integrals and reduce them to a basis. This basis we refer to as the master integrals. And if you know the master integrals, then you can write down any other integral within this family as a linear combination of said master integrals. The point I really want to make in the context of the spinning calculation is that, of course, the non-spinning calculation had already been done at 3 p.m. by Zvi Bern and various collaborators. The point is that the basis of masters that you need in the spinning calculation is exactly the same as the basis of masters that you need in the non-spinning. So if you've already done the non-spinning calculation at 3 p.m., essentially it's a solved problem. You just take the same basis of master integrals and you recycle them into the calculation. And that's it, you're done. So it's a very simple process to calculate these observables. But then when we get these results for the change in the momentum and the change in the spin vector, we then have to look at a number of consistency checks. The first is we need to make sure that all of these 1 over epsilons cancel at the end of the day. This is very non-trivial, and I can tell you that because it didn't happen the first couple of times we tried this. But what's also really important is these SUSY charges, which I mentioned. So we need all 4 of these SUSY charges to be conserved over the course of the motion, which again, that corresponds to energy conservation, spin supplementary conservation, and spin length conservation. So one example of what that looks like in practice is for energy conservation. We've got this 3 p.m. delta P component, then we've got the 1 p.m. and the 2 p.m. delta P components. They need to satisfy this non-trivial relationship amongst themselves. And that's something that you can check when you've done the final calculation. And if it doesn't work, then it means you did it wrong. So delta psi on its own is not really the most useful thing. What we really want is the spin kick. So that's the change in the Pauli-Lubansky spin vector. But in practice, that's moving from one to the other is a straightforward process. So we write the spin tensor in terms of the spin vector, as I said before. And using that, you can figure out what the change in the spin tensor is in terms of the change of the spin vector. Similarly, we know how to write down the Pauli-Lubansky spin vector in terms of the spin tensor. So we can write down a formula which gives us now the spin kick. So in essence, if you know delta psi, that's equivalent to knowing delta S and delta A. They're all just different manifestations of what is, in essence, the same physical quantity. And what we're finally left with then is a set of results, which unfortunately I'm not going to be able to give in full because they're very, very long. So I'm just going to give you a schematic form of these results. What we have is a situation where we have the different, so we sum on the different spin powers, and then we have the different mass sectors. And you can see we have this arc-cosh gamma function, which is familiar also from the non-spinning calculation here. And this shouldn't be surprising at all because, like I said, we're using the same sort of integrals to do spin as we did for non-spinning. So it shouldn't be any surprise that we see exactly the same sorts of transcendental functions appearing in the final answer. But we only see this arc-cosh gamma function occurring in the comparable mass sector. So if I go back a couple of slides, that's these diagrams here. So these ones give rise to the arc-cosh gamma function. And generally, those are the more difficult integrals to do. These guys do not give rise to the arc-cosh function. And so just to give you an example then of how one of these results actually looks in practice, what we can see is that the impulse, so this is the test body limit. So we're thinking about small m1 compared to large m2. This is the linear in spin part of delta p. You see we now have an answer, which is a rational function, which depends on the velocities of the 2 black holes, the initial Pauli-Lubansky spin vectors of the 2 black holes, and the impact parameter, the relative impact parameter between the 2 black holes. And what I've done here is I've decomposed it onto a basis of vectors. So I've got B, I've got my 2 velocities, and I've got this really useful vector L, which is essentially, it points in the direction of the orbital angular momentum. So if you imagine you have planar motion, this thing then basically just points out of the plane. And it's a useful way to define the 4th direction in this theory. And so this is what delta P looks like. And of course, for higher spin and the different mass component, we have a whole bunch more of these formulae, which you'll have to look at the paper to see all of them. So now I've looked at the more general case. Let me now specialize to the very interesting case of aligned spins, because now I can actually write something on the page. So if we have aligned spins, in that case, what we're thinking about is a setup where the spin vectors are pointing out of the plane of the motion. So they're orthogonal to the impact parameter and the incoming velocity. So they align with the orbital angular momentum of the system. In that case, the entire motion can be classified in terms of a scattering angle, which I get basically just by taking the mod of delta P. And of course, there's no spin kick anymore. The spin kicks are all 0 in this case. So I have a number of variables that this thing depends on. I've got the total mass, I've got the symmetric mass ratio, and I've got P infinity, which is the momentum in the center of mass frame. And you can see now I have these results for the scattering angle. So this here, this first line, this is the 3 p.m. scattering angle in the potential region. That's something I should have mentioned earlier. This is the 3 p.m. scattering angle in the potential region, which had already been computed by a number of the other groups. And these two now are the extensions to include linear effects in spin and quadratic effects in spin. S plus is the sum of the lengths of the two spin vectors, S minus is the difference. And these SE coefficients are related to those finite size coefficients. If you want to think about black holes, you can just set them to 0. Now, one thing I didn't mention, and I should have mentioned before, is that this is only in the for the conservative motion. One thing that we need to think about is we need to look at radiative corrections. But in the case of the aligned spin motion, there's this rather neat trick, which is we can use this linear response formula to get the radiative part of the scattering angle if we simply know the radiated angular momentum in the problem. This is known as the linear response formula written down by Bini and Damour. And what's very important is when we write down the complete scattering angle, including the radiative corrections, using JRAD, which we got from the waveform I showed you a few slides ago, we have an answer then which is finite in the high energy gamma tends to infinity limit, which is a very important property. And this basically then follows the same story which we had in the non-spinning case for this problem. So let me see, how many slides I got? Okay, yeah, I'm nearly there. So we can then start to look at some observables that we can get from our scattering. So we know we have these mappings between bound observables and unbound observables. I think probably the most famous now is the one between the scattering angle and the periastron advance. In the aligned spin case, it works exactly the same as it does in the non-spinning case. And all you do is, in addition to flipping the sign on the orbital angular momentum, you now also flip the sign on these spin vectors. And that gives us a formula for the periastron advance. I'm not going to go into this in too much detail, but there is one little thing you need, little annoyance with this, which is it turns out that the free PM component here actually cancels. But one thing that you can do is if you know the free PM component of the scattering angle, so this is coming from the impetus formula, what you can actually do is you can use that to learn the leading PN part of the 4 PM scattering angle, which then gives you something which you can compare with the PN literature. Another thing that we've been able to compute is the binding energy for circular orbits. And this all agrees with the state-of-the-art 4PN spin squared results, which were Jan Steinhoff and Michel Levy. So just before I finish now, because I think I'm basically out of time, I now am delighted to show you some new results, which we've actually just computed last week while we're here at KITP. So I mentioned that everything we did before was only for the conservative scattering. So we did our integrals in the potential region. Now what we have been able to do is we've been able to upgrade this calculation to the full inclusion of radiation reaction effects for the complete observables, delta P and delta A, for fully arbitrary misaligned spin configurations. How did we do that? Well, there were two new ingredients to the calculation. The first is we needed to include these kinds of self-energy diagrams, which the amplitudes people sometimes call these mushroom diagrams. And the second is we upgraded our integration procedure to involve these kinds of retarded graviton propagators. So now we have a preferred time direction associated with this I epsilon here. So now what we have is non-conservative scattering. So we no longer have momentum conservation. We have P mu rad. And this radiated form momentum is exactly the radiated form momentum which I showed you several slides ago when we were talking about the waveform. But what's great is that whereas when we were looking at it back then, I told you we didn't know how to do those integrals in PM. Now we do know how to do the integrals in PM. So what I can now do is I can write down a formula for the radiated energy produced by the scattering of two spinning black holes with arbitrary spin orientations. And if you do a PN expansion of this thing, then what you find is it precisely matches the formula which I showed you, which we computed from the waveform. And again, because the basis of integrals that you're using is pretty much the same basis of integrals in the non-spinning case, you see that the answer looks very similar to what you have for the non-spinning. It's just now that these free functions, F1, F2, and 3, these are now non-trivial functions of the spin vectors and the velocities in the system. Finally, now that I have this radiated energy produced by the scattering of spinning black holes and neutron stars, I can use that to map and find the radiated energy produced in bound orbits, at least for aligned spins. We don't know how to do this for misaligned spins. So I think that's probably me out of time now. So hopefully I've persuaded you that this WQFT provides a really natural, very streamlined approach for calculating these sorts of gravitational observables involving spinning black holes and neutron stars. So far, we've only gone up to quadratic in spin. We've been interested in pushing the PM scale while staying fairly low in the spin scale. One thing I didn't talk about is that at 2 p.m., we have this really nice scalar, the iconal phase, which is a single scalar which allows us to obtain the impulse and the spin kick. They're all encoded inside this thing. This is something that we also want to try to understand at 3 p.m., but we haven't done it yet. I also said at 2 p.m. we've got the gravitational waveform for scattered black holes and neutron stars, which gives us the radiated form momentum, the radiated angular momentum. And at 3 p.m. we have the deflection and the spin kick and the scattering angle, which we have now upgraded to include full knowledge of the radiation reaction involved in this process. I think our next steps are fairly natural. We know that there's been an awful lot of really interesting progress in the amplitudes arena lately on higher spins, and this is something that we want to look into as well. And we also, of course, want to think about higher post-Minkowskian orders. So if we could do spin at, say, 4 p.m., I mean, that would be very, very cool. We're also interested in things like tidal effects and other sorts of deformations that we can include in our action. And yeah, I think that's basically it.
Thanks, Gustav. Do we have questions?
Hi, so thanks for the nice talk. I know you said you were mostly concerned with pushing PM, but now as you start to think about going to higher spins, do you also expect that the basis of master integrals are going to be the same as you push to higher spin? Like this, you can see already to be the case.
I think so.
Cool.
I'm fairly sure that is the case. Yeah.
Okay.
Thanks for a nice talk, Gustav. Can you comment a bit more on the energy loss at 3 p.m.?
This formula?
Right. So does it have the same issues, I assume, that Gabriele was describing about the high energy limit, things like that?
I don't know. We haven't looked into this yet. I mean, I only found out about this issue from Gabrielle's talk a few days ago, so we just haven't had time. This is something that we can look into and chat about at some point.
Okay, thanks.
Can I ask? I'll go first. I have the microphone. So. I want to ask more on the supersymmetry. There was a psi and psi bar Grassmann vectors. So the bar there is, I mean, that's basically an R symmetry index.
Complex conjugation. That's
okay.
It.
How would you go to higher spin? Would you have more of these psis?
Yeah, so what we would do is, well, actually, so the inspiration for this and the title was this SUSY in the Sky paper by Gibbons and collaborators. What they were looking at is just linear in spin, and they just had a single real psi. So you can think of this complex psi as just being the same as two real psis. The way you would go to higher spin is you'd now just add more and more flavors of this thing. So what you do is you take the S mu nu and you'd write it now as a sum on flavors of an outer product of these two psis. That would be the procedure.
So you stole my question. But yeah, on the same thing, I was wondering if something special would happen if you take the spin very large, like go to the classical limit, you know, infinite number of supercharges.
I don't know. I mean, so in general, we know how to write down this theory for arbitrary spins in the case of a particle not coupled to gravity. And then it's just, you just have more and more of these psis, basically. In the case of the coupling to gravity, that becomes a little bit more tricky. But yeah, I don't think I have a good answer.
Maybe just a comment. So SUSY beyond n=2 is not really understood completely on the world line, because if you in flat space, it's trivial, but in curved space, for generic backgrounds, you don't know how to write down an action beyond this one. And I think the solution is that you only have this approximate supersymmetry. So you have supersymmetry only up to terms of higher order and spin. And then going to all orders and spin is highly non-trivial.
Well, maybe I can just say a bit more. So yeah, I mean, I guess you expect that there's going to be something, complicated because, but certainly if you have constant amplitudes, there's clearly going to be some ambiguities, high spins, right? But at least at at the level of the 3-point amplitude, something nice should happen. I think it might provide some insight on Compton. Yeah. Yeah. Yeah.
So moving to this slide reminded me of a question I'd had, which is when we think about black holes, you were commenting that, maybe you don't think about these finite size corrections. So just wanted to ask a little bit more about that. I know that, the love numbers, for example, of black holes are sort of considered to be 0, but they do, for example, have spin quadrupole deformations where the black hole picks up a quadrupolar deformation if it's spinning. That would then couple to its companion, and that is a known 2pn effect. So I guess the punchline is, has that already been incorporated in all of that? And also, do you expect to have finite size corrections even in the case of black holes that you'll need to start putting in here?
Yeah, I mean, we've not incorporated that here, but it's very straightforward to do so, I think is the answer. I mean, all that these effects really do for our theory is they just mean adding more interactions to the theory with just, more of these coefficients that one would put in front of such interaction terms. So the essence of the calculation wouldn't really change. We haven't done it, but I don't think it's a difficult extension to make, is the answer.
Okay, thank you.
We have Paolo on Zoom.
Yes, I don't know if you are aware that in the case of the string, you have the Navier-Stokes string, which is n equal 1. And then there exists also an n equal 2 string, and also an n equal 4 strings. So can you try to use n equal 4 to get a higher spin? In the case of string, you can do. I wonder why you cannot do for point particle.
I'll try to answer that question. I mean, Jan may also want to answer, but yes, you can do an n equals 4 extension of this theory. To the best of my knowledge, this works in a flat background. But Jan, do you want to take that one?
Yeah, so the n equals 4 spinning superparticle exists, but it needs an Einstein manifold as a background. So you can't do it on general backgrounds. And that's, of course, not in our interest. I mean, we want to have unconstrained backgrounds.
It's strange because in the case of string, you can do. The only problem that you get a negative critical dimension, but otherwise...
Wait, negative critical? Oh.
Yes.
It's also a little bit critical for us. We want to stay in 4.
No, n equal 2 gives 2-dimension or 4-dimension. Instead, if you go to n equal 4, you get -2. So that's a problem, but otherwise you could do. I mean.
I think so. In the 3 p.m. results, if you turn off the finite size effects, do you see anything, an enhanced structure in the spin that shows up? Like, for example, in the 2 p.m. result, the q dot s and q squared s squared, they're linked, and they're broken by this finite size effect. That's also there at 3 p.m.
Is this related to the shift symmetry? This,
yeah,
exactly. So yeah, I don't know is the short answer. We've looked at this at 2 p.m. We haven't looked at it at 3 p.m. yet. It definitely works at 2 p.m. So the easier way to look at it is actually by looking at this iconal, which I didn't mention. I only mentioned very briefly. In principle, one should be able to see that for p mu at 3 p.m., but we haven't looked at that yet. Definitely on the to-do list. It's something that's very interesting to us.
Anyone else? Okay, I think with no further questions, let's thank Gustav again.